I've been tinkering with Linux, vulkan, Bash, etc. And since January, I've been doing work on Zink. So some of the things I've been doing are emulation for a bunch of legacy features, for example, gel point for Q2, or edge flags, broken vertex mode, and other features. And one of the things that I've been doing for a while now is Uber shaders to reduce stutters. So the problem we're facing is in OpenGL, there are a lot of ancient legacy features that are controlled by state. So for example, things you said, well, GL set something and that something affects some feature that doesn't exist anymore in hardware or just Vulkan doesn't expose that you normally do with shaders in Vulkan. And so like nowadays, those things will be done in shaders. So Zink has to emulate those features with shaders. So the problem is state can change at any point. We can't predict how it will change. And this means that when we draw, we might have to compile a shader variant to deal with that particular combination of states, that particular state at that point in time. And because we only know, we can only be sure about the state when we are drawing, we have to do this right before drawing, and therefore we get stutters. So we would like to compile those shaders ahead of time. The problem is, as long as we use variants, that is different shaders for different cases, the number of shaders we need is pretty huge. And another thing that's pretty bad about OpenGL is that all those features can work together with like user shaders. The shader the user can send its own shaders, and those legacy features need to work on top. So this means for every shader the user sends, we will have to compile a number of variants. This makes the problem a lot harder. So Zink so far has precompiled the base variants, which works great when the application doesn't use any of those legacy features and there's no emulation needed, but otherwise there's absolutely nothing. So to improve this, Uber shaders could be a solution. So the idea behind the Uber shader is that we have a big shader that can do things that would normally be done by more than one shader that would be smaller, and we have a way of dynamically controlling this big shader, which means this one shader can deal with multiple states by sending the appropriate arguments to it, the appropriate data. So the advantage is we don't need variants because this one shader deals with everything, so we can precompile it. The disadvantage is that it can be slower. So this shader, because it has to deal with different cases, is going to have branching, and also it's going to be bigger, and therefore it's going to have more register pressure. The occupancy is going to be lower. Also, it takes longer to process and compile, and this is not something we can fix. But to get the kind of best of both worlds, what we do is we compile the Uber shader as soon as we can. So as soon as we get a shader from Gallium, we just start compiling using utilq. So Mesa has a very useful set of utility functions that basically deal with a queue of work and worker threads for it. So when we draw, if we start by using the Uber shader, so because we don't have any variants for that particular state, so we don't start. We don't wait for shaders to be ready. We always draw without starting with the Uber shaders. But when we do that, we kick the compilation for a variant for that particular state. And so next time we draw, the first thing we do is we check if the variant for that state is ready, and if it is, we switch to that variant. So eventually, we don't use Uber shader. The idea is the Uber shader is going to be used for a few frames instead of stuttering, but then we go to the variants, to the optimized variants that perform just as well. So we get the best of both worlds. We get performance and stutter free. So in practice, there are many challenges to overcome. So first of all, as I said before, we don't have the luxury of just creating shaders. We are not just dealing with the fixed function pipeline here. We're dealing with all of GL. GL mixes programmable shaders with programmable stages with non-programmable stages that are configurable. So it's really about passes. The emulation is done by passes that add the emulation to the user shaders, which means the Uber shader is really a Uber shader pass. It's basically the user shader would do a bunch of passes on it that would be done that normally would be done based on the state, but we do all of them unconditional in this case to get an Uber shader. But we need to control it dynamically, as I said before. For this, sysvols are great. Sysvols are just intrinsics that load a particular value, and we can lower them to whatever we want. So for the Uber shader, we lower them to push custom slows. For optimized variants, they're just we just align the value if we can. Or sometimes you can also use push constants for variance to reduce the number of variants we need. So we need to change the existing near passes to make sure that, first of all parameters they need are passed using sysvols and not for any other mechanisms. So, for example, Gallium has state tokens. Those are not usable for us. We need sysvols. Also, all passes need a way of being dynamically disabled. And this is because we're doing all of the passes, but some features need to be disabled sometimes. And sometimes this is implicit. For example, for alpha test, we can just set the test to always and does nothing. But in some cases, we need to change the pass to add some conditional inside it. In some cases, that's not enough, and we need to rewrite it. And an example of that is near lower flat shade. So it's a very simple near pass that just changes some attributes and some variables to achieve flat shading. But this can be changed dynamically. So the solution that I have consists of duplicating variables that need to be flat shaded and having different attributes in the copies so that we can then BC cell between them in the fragment shader. This is where it gets funny because, so there are rules about interface matching, and they're such that you can't really predict what the fragment shader will look like. Like you can't predict which slots it's going to read, because there are some slots that are not passed through, some that are. So in order to deal with this, the way I'm doing it right now, I'm just taking every slot and assigning it to slot times 2, and then the odd slots are free, so I can add my own variables. The obvious problem is called the hybrid shader slots, but we don't have infinite rooms in this case. We can run out of slots. So this is a temporary solution, and really we do that with a vulkan extension. There is a vulkan extension that exposes all of the attributes and barycentrics, so you could do we could do the interpolation ourselves or not do it for flash shading. It's not clear to me whether this spec says it has stable vertex order. I know for a fact that some implementations don't, and it's not widely available, so Radvi only implements it starting from RDNA, I think. So this is a bit of an open problem. Another problem is called near pass-through GS. This is a geometry shader that, as the name implies, is supposed to act like a pass-through, which is surprisingly hard, because when you enable geometry shaders, a bunch of features just don't work anymore. You need to emulate them. Also, there are other geometry shaders that are used for emulating quads, for example, and there are also passes done on geometry shaders. So the problem is this pass-through GS is created on demand. Whenever it's needed, it gets bound. This kind of messes with Zink's logic for GPL. So all of this all of the overshaded work works using GPL, because we basically compile all of the shader stages separately from other state. But because when pass-through GS GPL doesn't work, it means Uber shaders don't work. So this is a pretty big deal for us. This is not something I have a solution to for now. So now I'm going to talk a little bit about actually implementing this into Zink. So shader caching in Zink is very simple. As you can see, here's a diagram of it. It's really not. I'm going to try to break it down. So shader state gets created and bound by Gallium. And at drawtime, we need to start by looking for a pipeline. So we kind of go backwards. Usually you start from shaders, you have to do lowering passes, then you have to translate into SPIRV, then you create shader modules, then you create GPL, then you create full pipelines. But basically the way Zink works is when we draw, we kind of go backwards. So we start by searching for a pipeline. Pipeline are hashed by the state hash. All of the state of OpenGL is hashed incrementally. And so each time we draw, we can just look up a pipeline for that state. And when we find a pipeline, it doesn't end there, because pipelines are at first fast linked and then optimized linked asynchronously. So we must check if the asynchronous compilation is done. But when we don't find the pipeline, that's where we go backwards in the pipeline, backwards in the process. So we need to create a pipeline from the current program. We have to take the GPL for that for those programs, plus some state, of course. So programs are again fetched from cache, and the key in this case is the hash of the user shaders. When Gallium sends shaders, we hash them, and we combine the hashes into one, and we get a key for that particular set of shaders, and that's what caches the program. So to handle variant, the way Zink works is the same Zink program gets, this thing called Zink program that more or less corresponds to the GL program, but not quite. And when we need a variant, we update the modules on it. And obviously we need a new pipeline library for that combination of modules. So there's also a pipeline library cache. The caches might actually be filled asynchronously. So this is how precompilation actually works, by filling caches asynchronously. During steady state creation, we kick the compilation for the pipeline cache. And we add an entry to the cache synchronously from the same thread, so we don't need any locking. But the actual entry contains a fence. The idea is the worker thread is going to work on that entry of the cache, is going to do all the processing that's required, and it's going to signal a fence when it's done. And the idea is when we need a shader, we can either check the fence or wait on the fence and use it. It gets a bit funny because OpenGL actually allows to share programs between contexts. And the reason you might want to do this is in OpenGL, context can only be accessed by one thread. So for example, Doom 2016 uses a separate context to compile programs, which are then used by the main context. So to support this in Zink, what we have is basically a cache for the cache. When we create a program, instead of just creating a cache for GPL, there's a global cache that gets queried. So this makes sure that programs created from the same shaders end up containing the same cache. So we need to introduce Uber shaders into all of this. So this is no particular trivial. So there's also the case of separate programs that we need, separate shaders that we need to handle in Zink. Basically, in Zink, when separate shaders are used, GPL is created for each shader and then linked together. But this pipeline is then replaced in turn. And what happens is the program that was compiled from the separate shaders gets lost. So this didn't work for me. So I kind of changed a bit the logic to keep so that I could keep the Uber shader around in some structure. So I changed it so that we now have a program for each variant. A program now doesn't need a GPL cache; it only has one GPL because it handles one combination of shaders. It handles one variant basically, and for the cross-context cache, we only need one GPL, which would contain the Uber shader GPL. And now, in order to deal with variant cache, we now have a cache of programs. So for each variant, we have a program in a cache. But we also have a fast variant for the base variant, a fast path for the base variant. The idea is we don't want to do cache lookups to get the base variant, because now the program that gets bound is always the Uber shader. Sometimes we compile the base variant, we need to bind that, which is because it would be more optimized. But also, because this is going to be a very common case, this is actually a special path. And so the logic in general is if we cache hit, so the idea is if we look for a variant and we find it, we need to check if the fence is signaled, because it might actually not be done compiling. If it's not signaled, then we can fall back to the Uber shader. If it is signaled, we can use the variant. But if we miss the cache, it means we haven't even started compiling a variant. So that's when we kick compilation for the variant. So this means that the draw starts compiling a variant, but asynchronously. It only kicks the job. This is actually more complex in practice, because compiling a variant actually requires a few steps. First of all, if the program was created from separate shaders, we need to replace it. So we need to wait for that to happen, which means we delay by, say, one frame or one rocal. So then we need to run the compilation pipeline. So do all of the lowering passes for that state, and do spirf to nerve and get the spirf code, pass it to vulkan, get the shader module. And we need to create a GPL for the set of shaders. So the way this is done is each of the stages is synchronous. So the idea is each time we draw and we request a particular variant, we check where we are in this kind of pipeline. So we go through them, we check the fences. When we encounter a fence we haven't signaled, we keep the job for that particular stage. And in the end, when all fences are signaled, means we've done all the steps, we can use the variant. So in the current state, the Uber shader supports the following features. So gel clamp, clip planes, fragment color clamped. Alpha test and flat shade, which I talked about, is work in progress. I'm probably not gonna merge it at first. So when I worked on this, I started by not really caring about upstreaming it, so I had like 80 commits. It was kind of messed up. But now there's a merge request which has about 60 commits, so it's not the full patch, but it's what I want to merge it first. So I want to merge what I've already worked on cleaning, and then after that I can go back to the other branch and merge more stuff gradually. So in order to use supershaders, there are some requirements. So first of all, we need GPL. So all the stuff that's required in Zink for the optimal path. Zink basically has this big divide between optimal path and non-optimal path based on feature set. We need the optimal path, so GPL, dynamic state, and other stuff. We also need 256 bytes of push constants. The reason is because in order to emulate GL clamp, we need to send sampler state to the shader, which is pretty big. And actually, I'm still not dealing with bindless textures, so that's not a problem. So I want to give some numbers of this patch. There's a pathological example. There's a trace used in the MSSCI, which is from OpenMW, which is like an open source recreation of Morrowind. And there's a point in that trace where a bunch of shaders get sent, and this causes stutter on pretty much any driver, but it's particularly bad on Zink, because each time a new shader is seen, Zink has to also compile the variant for it if that's required, meaning a shader might get compiled a number of times synchronously. So that's, you get like, without this cache, you could get like up to 193 milliseconds of stutter in that trace. So that's pretty terrible. With our own cache, we get 262 milliseconds. Now with the patches that I've made, at first I got 276 milliseconds with our not cache, which is not an improvement. So what's going on? Well, the shader cannot handle anything, and in particular, there is some emulation that's usually done by the state tracker, and there's some emulation that's done by Zink. I'm dealing with some of the emulation that would be done by the state tracker, but I'm not dealing with any emulation done by Zink. So when any emulation is done by Zink, the UB shader wouldn't be usable because it wouldn't produce correct results because it's not emulating those features. So even if a single feature is not supported by UB shader, you get a stutter. And plus we get some overhead. Because, as I said before, Uber shader is actually slower to compile, so that's why it's actually a bit of a regression. So eventually, we would like to support all features on Uber shader, meaning we can always use it. But for now, just for benchmarking, we're gonna use it anyway. We're gonna get broken rendering, but at least we can get some numbers. In this case, I've disabled this cache from Zink entirely. We go from 288 milliseconds to 317 without this cache, and with this cache we go from 262 to 221, so it's a small improvement. And I've actually rebased this patch recently, and apparently Zink has actually kind of regressed in a way. So now, even without the ACK that I mentioned, so even without using the Uber shader in all cases, we still get 50 milliseconds improvement. And with the ACK we get pretty much 200 milliseconds of improvement. Again, we still stutter because this game is just sending shaders. We'll never no stutter. Even in Radeon SI, you get like 70 milliseconds of stutter. But again, this is a big improvement from not having this patch. So currently, one of the things I'm working on is only starting compiling Uber shaders once they're needed at least once. The idea being, if an application never uses any legacy features, we don't want to pay the price for compiling Uber shaders. So we start by using the old logic of pre-compiling base variants, and then as soon as we need the Uber shader once, we start compiling those. This is actually very hard to do. You might end up with some programs that have Uber shader and some that have a legacy shader. So what do you do when you need a legacy feature for those programs? Do you stutter or do you compile Uber shaders synchronously? It's a lot to work out there. So I have some implementation of it, but there are a lot of details that I need to work out. Now I want to talk a bit about visualizing them, visualizing user shader in action. So a simple idea is just outputting red whenever we use the Uber shader. But this doesn't really work in practice because objects almost always would be covered or off screen. The idea is the game is not going to render stuff. It's not going to do perfect culling. So very often objects are rendering outside of the screen or cold. So by the time you actually see them, the Uber shader has already been replaced, so you don't see it at all. So what I came up with is this very simple pass that just calls discard on half of the pixels in a checkerboard pattern. And this way we can see through those pixels. So the idea is, on the Uber shader, we draw all pixels on a fixed color, which in this case is red. And on the regular variants, we discard half of the pixels. This way, if something is occluding an object drawn by the Uber shader, half of the pixels will basically just come through. So doing that means those pixels would never be written and cleared, though. So I also alternate the pattern to make it disappear eventually. The idea is eventually, without alternating patterns, eventually the entire buffer becomes red. Not the entire buffer, but like half of the pixels become red. You can't see anything. So by alternating patterns, I can more or less clear the buffer easily. So this is just debugging shader. So it can look like this because it also means that the previous frame kind of survives. The idea being, because I'm alternating patterns, if no Uber shaders are used, you're going to get a little bit of the previous frame and a little bit of the current frame. So it looks very broken. Because yes, I have a demo. You're going to see very broken stuff because you get those images in the swap chain that basically have half of the pixels that are older than they should be. So you get a bit of flickering, and but what you have to look for is red flashes. So every time you see a red flash, that's the Uber shader in action. So for this time, I use Poro, and right away you can see the whole screen is red when I started, and this is the case with pretty much any game because, as I said before, right now the Uber shader gets used for every object at first. For every draw call at first, because we don't have the logic to avoid compiling it. So the first thing you see is a red flash. And if I start going in game, you can see some objects flashing red. So those are being rendered with the Uber shader for those frames. You can see coming through, as I said. If you pay attention to the portal, first it will be red. Because again, at first you use the Uber shader. There's actually something very interesting that happens here. I'm going to explain it in some slides later. Okay, so I'm going to go back to the slides now. So first of all, this is something you saw. This trick that I did with the checkerboard pattern was to be able to see draw calls done with the Uber shader through other objects. And as you can see, this is working. We can see the Uber shader here. This is the portal that I talked about before. So now this is something interesting. You see this laser at first gets rendered with Uber shader. Again, because everything is at first. But later, you see it again. And the reason is those reflections are being done using user clip planes. And user clip planes are one of the features we need to emulate. And so this laser is being rendered again with user clip planes. This is an example where you compile a shader, but sometimes you need to introduce emulation in it. You'd have to stutter, but in this case, we can just fall back to the Uber shader again. So this is why it appears red as a red quad, because we're falling back to the Uber shader to avoid the stutter. So that's it. I can go to Q&A.
So with this visualization, what is the kind of improvement that you're hoping to make based on it?
So you mean like what's the best that you could get in theory?
And so we can visualize now, like, hey, when do we use an Uber shader versus not with this visualization, right? So like, are there any problems you foresee us being able to solve with this visualization?
Right, so the visualization is very flawed. Like there's, so you can't see where it's the first. Like you mean where you can't see where it's the first time, where we actually need Uber shader for emulation or not. So I didn't understand what.
So like we can see where the Uber shader is used right now. So like, is the goal here to see like, hey, can we see where it's used now, and we're trying to bring down where we're using the Uber shader, like using, for example, heuristics, or like, what's the next step here?
Right. So, sorry, I'm not managing to. I didn't understand the question. Sorry.
So like we have the Uber, we can visualize the Uber shaders.
Yes.
What are we going to do with that?
No, this is just for debugging. I just brought it here to show it.
Okay.
Now, yeah, of course, this is not in the merge request. This is not, you're not gonna find this. What you see, if I didn't do this hack, you just see the game running normally. You wouldn't really see the difference. I made this this pass just for the demo to see this is like what is this doing under the hood, right? So the idea is, where you would see a red flash, that would be a stutter normally, right? That's the idea of the demo. It's kind of what it's trying to show. When you see the Uber shader, it means there's one less shader that's being compiled there. That's the point of the visualization, right? I made it for debugging.
So just to try to chime in a little bit, I think that if you want to try to find out how to improve your applications to avoid this, a better approach for that would probably be to add some counters for whenever we're compiling variants or something like that, so that your application can kind of keep that under control. Alyssa just showed me the stop doing Zink meme.
Can I go?